We have a chair.
Welcome everyone to the first lecture.
Oh, got it. Thank you. Got it. Okay, so last time I told you about Frank's theorem. So let me start with Frank's theorem, and then the rest of the lectures are going to be more application oriented, since I've developed all this machinery over the last few talks. So remind you, the hypothesis for Frank's theorem, you have a finite CW complex, the action on homology, either all your eigenvalues are outside the unit circle. If you're an endomorphism, if you're homeomorphism, you're allowed to have, and in fact have to have eigenvalues inside the unit circle. You have to be careful. You can't just say hyperbolic map, because if you have an endomorphism with eigenvalues inside the circle, then you can't use the inverse, and the theorem, in fact, is false. Okay, so let's work just a minute ago. So here's some examples. What we've seen through the whole course, higher degree maps of the circle, linear endomorphisms of the torus are mapped on the wedge of two circles. There are lots of examples on higher genus surfaces. So here's the theorem, which I stated last time, but let me state it again. So you have your map that's H1 hyperbolic, and then there exists this alpha into a torus of dimension equal to the rank of first homology, such that you get this diagram commuting. So the image of X could be quite small inside here. There's no assertion about this being onto. And this toral automorphism is induced by the linear map, which is the action of F on H1. All right, so here's the proof, which I talked about last time. It's actually fairly simple. And here's the corollary, which is most people's image or remembrance of Frank's theorem, that if you have a map with a torus that's H1, so you just know its action on homology, then there exists, in this case, an onto map, which makes this a semiconjugacy. All right, so on the torus, you get a dead semiconjugacy instead of a map into the torus. So these are comments I made last time, and there's an intimate connection between Frank's theorem and abelian Nielsen theory, which hasn't really been recognized. And I went through this last time. Let me briefly review abelian Nielsen theory. If you have homotopy maps, you say periodic points or fixed points are homotopic if they have their lifts, equivariant lifts to the universal abelian cover now. So the whole theory is just like Nielsen theory, but now you use the abelian Nielsen theory. And the arc definition is the one you'd expect, but now this is zero in homology. So you conclude there's, because each abelian Nielsen class is made up of unions of regular Nielsen classes, there's finitely many of them, and you can have a collection of abelian Nielsen classes. Each is compact and open. So you can define the index. This is just imitating all of Nielsen theory quickly. If your index is non-zero, your class is essential, and collapsible classes are defined the same way. Your abelian Nielsen equivalent to something of lesser period. Then the fundamental theorem is just like the theorem of Nielsen theory. If you have an uncollapsible essential class and some given period, then if you're homotopic, then that new map also has a period Y, has a periodic orbit of period N, which is now in this case abelian Nielsen equivalent. Okay, so now what does this have to do with Frank's theorem? So let's stay in this situation where G and F are homotopic. And so since they're homotopic, they have the same action on H1. And so each one of them has a Frank semiconjugacy. All right, and so we want to compare, so that's been the whole theme of the course, is how much dynamics persists under homotopy or isotopy, or is detectable by the action on H1. So here's the theorem that I showed you last time in a special case, but having the same image under the Franks map is the same as being abelian Nielsen equivalent. Or in general, global shadowing just means that the orbits stay a bounded distance away in the universal abelian cover. Then this tells us that Franks map is exactly keeping track of global shadowing classes. All right, so points globally shadow in the universal abelian cover if and only if the image of the Franks map is the same. So what this tells us is that alpha of x is some measure or picture, just like the rotation set, but now it's not, isotopic to the identity, but it's a picture of all the asymptotic dynamics from an abelian perspective. All right, so this is, global shadowing is for all courses. And just like if you remember Handel's theorem set a point to the special point it globally shadowed. So that'll be the case here, that Franks map is just like Handel's map, but it's for abelian theory instead of a homotopy theory. All right, so the difference between these images will detect their difference in their dynamics. Now, we saw these wedge of the circle maps that I constructed were minimal in their homotopy class in terms of the amount of dynamics was there because they were tight and expanding. So if you homotope your kind of Franks set or not our abelian rotation set or whatever, I don't have a name for it, can only get bigger. All right, so that's the story, and there's lots of theorems and examples, but basically the moral of the story is that if you abelianize the theory, you go from Handel to Franks in a very precise way. All right, so this is just a curiosity. When you're preparing talks like this, you come up with various curiosities. I just thought I would raise it. You may have remember seeing this group come up all the time, many places. There's at least 3 ways it comes up. First, it's the collection of abelian twisted coordinates. So these are the coordinates assigned to abelian Nielsen classes. So the collection of all of them is exactly this group. If you suspend the map, then in fact, this is the main interesting factor in the homology of the suspension. There's a Z factor there, which is just the period. And I haven't talked about this, but it also turns out to be the deck group of the largest cover to which F lifts and commutes with deck. All right, so for example, on the torus, which as I've said last time, is a very special case where all the Nielsen classes are full and assume you don't have an eigenvalue of 1. So the importance of the eigenvalue 1 from this guy, if you have an eigenvalue 1, then you get a 0 down here. And then this group has a non-torsion factor, has a Z factor. But if 1 is not an eigenvalue, then the guy is pure torsion. So this is often surprising at first that these suspension manifolds of plural automorphism are mainly torsion, except for kind of the period direction. So in this particular case, I'm continuing to talk about the torus. So in the torus, the set of fixed points is exactly this group. So this is another curiosity or another nice feature of the torus, that for any period, the set of fixed points, in fact, is a group. It's a subgroup of the torus as an abelian group. So this comment is just to explain, so this is saying more about why this group is important. So for a general H1 hyperbolic map, our strategy is to stick it inside a toral automorphism. And for the original map, it has some abelian behavior, and that's mimicked by the image inside the torus. We fill some of the Nielsen classes of the torus, the abelian Nielsen classes, which are the same as the Nielsen classes because the H1 is equal to pi 1. So again, I said this is just a curiosity. These days of computers, you can do this stuff. Is what do these groups look like? Okay, so again, this is mainly a curiosity. I don't know what this all means, except it's easy to compute. So here's the action of our one example. And for various periods, so various periods, you get abelian Nielsen classes of various periods. These are the groups, right? There's no, one is not an eigenvalue, so these are pure torsion. Compute these with the Smith normal form, if you remember that from your simplicial homology, if you did that. Here's our favorite 1, 2, 1, 1, 1. So if you think in terms of fixed points, the collection of fixed points of period 4 have the structure, there's 45 of them, the product of these, and have this structure as a group. And again, I don't know what this all means, except I find it very curious. Here's just another example of a, well, this is a toral endomorphism. These are what the groups are. And I just end with this curiosity question. As I said, you prepare things and you say, what in the world is that? Well, anyway, so this says, what in the world is that? Okay. So where did a lot of this came from? Something I haven't told you about, which is an idea of Albert Fatih in answer to a question of Hirsch from 1970. So Hirsch's question, and some people attribute it to Smale, was if you have a linear toral automorphism, what kind of compact invariant sets can there be inside the toral automorphism? And there's fair amount known about this, but in terms of their lack of smoothness and arcs and subtories, I'll tell you a few results related to this program. But the question that Fatih studied was whether you can have an embedded manifold as an invariant subset of a toral automorphism. And it was known that it can't be very smooth. You know, it can't be, certainly can't be differentiable, and if there are like limits to even Holder exponents. All right, so what was Fatih's idea? Well, the Fatih's idea was to use a Frank's map, is to start with a pseudoAnosov map on a higher genus surface, and it's H1 hyperbolic. And then you take the Frank's map and you send it in, if it's genus G, you send it into a toral automorphism. The action on H1 is, it gives the hyperbolic toral automorphism. This guy sits inside. It's clearly a compact invariant set. All right, so the question is it a manifold? In other words, the question is this map 1-to-1 or not? So the whole program and the whole answer to the question centers and is dependent on whether the Frank's semiconjugacy is 1-to-1 or not. So the image doesn't have double points or triple points or singularities, or is it genuinely embedded? So Albert proved some nice results about it. It's finite to 1, it's locally 1-to-1 against the singularities. He gave some estimates on various forms of dimension of the image. Gavin Van showed that alpha is in a special case. If phi has just one singularity, it's never 1-to-1. Bargen Quapis showed it's 1-to-1 almost everywhere with respect. There's a natural measure for the pseudoAnosov. So what does this have to do with what I've been telling you is that the whole program can be reframed in terms of global shadowing. So this alpha is injective. Remember, if and only if the image of alpha is exactly detecting global shadowing. And so the question of alpha being injective is exactly the same as whether you do, well, it's injective if and only if there are not 2 points which globally shadow in the universal abelian cover. So the thing about pseudoAnosovs is they definitely won't shadow in the universal cover because you have expansion and contraction there. So this is just reframing the question in terms of abelian Nielsen equivalence. Okay, so the one reason I started to think about these lower dimensional wedge examples, partly because they're easy for exposition, but also it's a baby version of Hirsch's question. So the question is, could you have a map of the wedge of 2 circles or more than 2 circles which embed in a toral? In this case, it'll be a toral endomorphism. It'll be non-injective. Okay, so here's the question, is whether you can do that or not. I just said that in words. And I fooled around with this numerically for a little while and didn't solve the problems. So here's some, so here you got a lot of, these are just some various random endomorphisms of the wedge of two circles. Here's some pictures. You can see there's lots of intersections. Here you see less intersections. So anyway, so that's just a question. And I think it's completely doable, but I haven't done it. Okay. So the next step here is to really squeeze the juice out of Frank's theorem. So thus far, we've had the entire spectrum be hyperbolic. Okay. But now what happens if you just have one eigenvalue off the unit circle? What can you grab or use or deduce from that? So it turns out just using the same basic argument with series, you can squeeze a fair amount of juice out of each hyperbolic eigenvalue. All right, so that's where we start. And now to the relief of the audience, you will have some slides that are typed. Okay, so this is a reminder, the setup we're going to use. I did this last time. We're working in the universal abelian cover. We stick it inside the appropriate Euclidean space with dimension equal to the rank of H1. And I use a basis of forms, I stick it inside. And after we do that, the lift of a map acts like a linear bit, which is action on homology, plus a bounded bit. The fact that this is bounded, as you remember, is important. So the conclusion, if you like coarse topology, which is the big thing in Florida, is that coarsely or on large scales, the lift of any map acts like homology because this bit is bounded. So if you look at anything in the universal abelian cover stuck inside the Euclidean space, stand back far enough, it looks just like the action on homology because this guy's bounded. So depending on how far you are away from the linear automorphism or how big this is, you have to get further and further away to make it look like the homology case. Okay, so this is our friend, the universal abelian cover, and we want to use this to do a Frank's theorem, but just for each one. All right, so let's just assume we have one real eigenvalue. All right, it has an eigenvector. Let's make it simple to make life simple. We have some lift to the universal abelian cover. And what we just learned is that it acts to big scales. It acts like the action of the linear map. So that means that in the direction of the eigenvector, you have growth, you have expansion, and orbits are moving at this rate. All right, so the idea is to basically just do Frank's, but instead of the entire matrix, just normalize. But now this is the projection onto the eigendirection. We normalize that, okay? So let's see how you implement that. It's the same scheme that I've used twice here. Here's our map. We do an induction on this and we get this formula. And now we're just interested in our one expanding direction. And so I project in that direction. And when we do that, we're just using the eigencoordinates. So this just becomes multiplication by mu. And here we have the projection of the bounded piece. And we take our limit. And once again, this guy converges because this is bigger than 1 in norm. And this guy's bounded. All right, so we've done the same scheme that I've done for you a couple times, but now I'm just doing it for a single eigenvector by using the universal abelian cover, sitting in a big Euclidean space and just projecting onto the eigendirection. All right, so what that means is, once again, we write this down, and now we get a semi-conjugacy. But the important point is now it's a semi-conjugacy in the universal abelian cover to multiplication by R, by mu. In other words, you have this guy here, whatever it looks like, and it's semi-conjugates to multiplication by mu. All right, so it's all happening in the cover. Okay, that's the downside of this whole thing. At least a priori, everything's happening in the cover, and it's not going to go down to the base, at least as the semi-conjugacy. Whoops, okay. You can see this film picture. Okay, thank you. All right, so here, oh, I had the picture in my slides. Sorry, I could have just not drawn it. So we have a semi-conjugacy from the cover to multiplication by mu on the line. So it's telling us, that this is, things are growing in these two directions, but it's giving a precise description of that. All right, so that's what you get. Now, we want to take this and get information in the base. All right, so these are just some comments here about, as I've said a couple times, you don't expect this thing to be very smooth. And that's certainly what Fatih found and other people have found in other examples. So in general, we'll have theorems about how smooth this is in certain cases, and it's going to be Holder, but not very Holder, nowhere locally one-to-one, all sorts of stuff. This is not so important. There's a general theory of these. It's an eigen cohomology class. One thing that I'm not talking about is complex eigenvalues and repeated eigenvalues where you have non-trivial Jordan blocks, but you deal with all that in the, it's a royal pain, but you deal with it. All right, so here's a statement of the theorem. As I say, the argument goes back to Frank's, and Mike Schub had a paper using Alexander cocycles, which basically does something similar from a very different point of view. Here's the statement of the theorem. Let's stick to the homeomorphism case. We have a smooth connected manifold. We have an eigenvalue, either real or complex. It's a simple, turns out it's easier to work with cohomology. It has norm different than 1. And then for each lift to the universal abelian cover, there exists a unique map which semi-conjugates according to the picture. All right, so the semi-conjugacy, of course, depends on the lift, but here's our basic formula, all happening in the universal abelian cover. All right, so that's their theorem. And the next question, I've already kind of answered this question, is how do you push this thing downstairs? Then you need to have a fully hyperbolic spectrum. All right, so this is the question, how does this collection of semi-conductivity descend? And this is the theorem that I talked about a few minutes ago, that if you have a completely hyperbolic spectrum, then the image sits inside a linear Nosov. All right, so we talked about that beforehand because that's kind of the easier case instead of working one by one. All right, so now the issue is what have we bought with this semi-conjugacy in the cover? And it turns out you've bought kind of more than you thought you might at first glance. All right, so the first thing you get is an invariant continuous decomposition into level sets. So this is all happening upstairs. So this is fairly obvious because we have a semi-conjugacy here. Then if you look at level sets of the semi-conjugacy, then they act according to this dynamics. Okay, so upstairs, you just multiply, this should be a cap X, sorry. And the nice thing about this thing, because it's built from homology, it actually descends. All right, so given just this eigenvalue off the unit circle in homology, you get an invariant decomposition downstairs. So if this was a linear Nosov, then it would just be the standard foliations. But this is one-dimensional, so we might think about, let's think about the two-dimensional case. All right, so that's our first structure, an invariant decomposition just arising from the action on homology. And of course, I'm saying nothing about the structure of these sets. They could be very wild. But it's an invariant decomposition, which if the eigendirection is irrational, it's going to be wrapping around this in an irrational fashion. Okay. So in addition to this, you get a transverse structure, which we're going to exploit later to the decomposition. So how do you do this? Well, you have a pair of points and you take an arc between them. Okay. And you have an arc between them and you define F mu of it. All right. So this is now a function. And it's a function on arcs in the universal abelian cover, which is the difference in the values of the semi-conjugacy. Okay. So because of the way this has all worked with cohomology and equivariance, it descends, in fact, to a way, I'll talk more about this, of assigning numbers to arcs. And also, if you go a different way there, you're in universal cover, so you're homologous down here. So you're getting a way to define a number associated with an arc that's homology invariant. So that means that you perturb this guy, if this new thing is homologous to that, meaning that the loop you make is zero in homology, then you get the same value out of this function F. All right, so this is some kind of transverse structure, and when we get to pseudoAnosovs, it's going to be, it's going to be a transverse measure or a transverse Holder distribution, holonomial invariant. We'll say all that to come. All right, so this is the main object I want to think about, because this is the thing that builds the structure. So a path cocycle is a map from the arcs into, this is just some general field, it's usually C or R, that it's additive. All right, so this guy back here is certainly additive. If you do this and then this, you just add these two differences. And this is the homology invariance. All right, so for example, in the genus 2 surface, this curve from here to here and this curve from here to there are actually homologous. So they get the same value by this arc path cocycle. All right, so this is just a definition to tell us what kind of structure this thing that we've bought with the single eigenvalue outside the unit circle. All right, so this is just some jazz. It represents a cohomology class. If it gives the proper value to closed curves, you act on by the function and the thing. So our cocycles will be eigen under this action because of exactly this picture, because this distance gets expanded by mu, sorry. And so it's going to be eigen. And this is a generalization of what you usually do in Durham cohomology. If you have a closed one form and you integrate an arc along it, it's going to satisfy these two properties. If you integrate and then integrate, you get, the sum, and it's homology invariant because the one form is closed. All right, so in some sense, in a very precise sense, which I won't get into, is the collection of path cocycles expands and generalizes and completes the collection of closed one forms. All right, so that's all to come. All right, so this is just reframing the semi-conjugacy in the cover, which seems maybe not very useful, to something in the base. All right, then here's the formulation, which should be plausible, since I waved my hands at that picture. So this is the same theorem recast. We have a continuous map and an unstable eigenvalue, and its eigenclass in now cohomology is this. Then there's an eigenpath cocycle which is eigen. All right, so we've taken a single, eigenvalue off the unit circle and built this path cocycle that's eigen. All right, and as I said, it follows from the construction I did already. Now you might want to wonder when there's actually a one form. So a one form would mean you have a eigen one form. So the image of the one form is the one form, but expanded. So it's very rare. It's true for pseudoAnosovs where the kernel of the one form gives the foliation. All right, so it's very rare And as I said, we've completed the space, right? So you don't have an eigen one form, but there's always an eigen path cocycle. Okay, so as I said, we've expanded the space of closed one forms to include objects with much less regularity. We'll see they don't have much regularity at all. They're Holder anyway. But in this wider class, we have an actual eigenvalue. You know, what a one form will do, if it's an eigenclass in H1, it'll be, you'll multiply it, but then there'll be another term, the D of something, because it's just a class in cohomology. Okay, so these are our objects. So I want to use these guys to do our whole theory of the semi-conjugacy, because I'm going to use these guys to build structures for pseudoAnosov maps. So, you know, this, in some sense, these guys are very general, but I need to beat around with them for a while so I can apply them. All right, so what's the connection to the equivalence relation or the decomposition of the space? All right, so the connection is you define a relation on the manifold by 2 points are equivalent if there's a path between them which has, quote, length 0 with respect to our cocycle. All right, so this gives a equivalence relation. The classes define a decomposition. And if you just trace through the pictures and the definitions, it's exactly just a different way of constructing the invariant decomposition from the map and the cover. All right, so if you have an eigenpath cocycle, which comes from, again, the action on H1, and it's our invariant decomposition. I've made this comment already. They can be pretty wild, but let's apply this thing to a particular fairly rigid class. So this is all the abstract topology, and you can get some things out of it. But now let's specify where we have a lot of structure and see what these, what these eigenvalues off the unit circle actually buy us for something where we have a lot of structure. And just some reference things, path cocycles, they're in some form in a paper of fatigue. Farber has a whole bunch of theory of topological one forms, which are the same object defined differently. Okay.
I'm a little bit lost.
I'm sorry.
Paths are loops.
Yeah, right. So
To represent cocycle.
So the path cocycle, right. So I'm not developing the full homology theory, but the path cocycle just defines a map from paths to R. Okay, so it's a general object. Now its connection to cohomology is that if you do have a closed loop, then it's going to assign a number there, and it represents the cohomology class if this is the same number that the cohomology class would assign it. Or if you like, if you're thinking about one forms integrating a closed one form.
I like to look at it as index of intersection.
Yes, right. So that,
with other loops.
yeah, index of intersection, or even right, but that's a discrete version where this is going into Z. You can think of cohomology as intersection number with this basis. All right, and then that's a discrete version of this, and you have to complete it. All right, so that's what these guys are. I'm not doing the whole cohomology development.
You mentioned braid. At some point.
Yeah, so let me get a little further and have a break. Thank you.
Then we get there.
Okay, so let me define pseudoAnosov maps and then we'll see. So I've talked about these before. Many of you know what these are. Just briefly, whereas a homomorphism of a compact surface is pseudoAnosov as a pair of invariant foliations. Foliations have singularities, stable and unstable direct foliations. And the hyperbolicity in this case is not given by the derivative, but rather invariant measures. So there's a measure on transverse arcs. You see why I'm talking about transverse arc objects. There's a measure on transverse arcs which doesn't change as you slide along, and under the action of the map, one foliation that expands, the other foliation that contracts, and of course you have these fixed points as well, or periodic points. There's a finite number of singularities. All right, so this expansion and contraction has a name called dilatations that's connected intimately with the topological entropy. We allow one prongs, which puts us, well, so it's a generalization of pseudoAnosovs, which have no one prongs. We allow one prongs that allows us to have pseudoAnosovs in the identity class, for example. All right, so this is all stuff about pseudoAnosovs. They have Markov partitions. Nice way to think about pseudoAnosovs is take your Markov boxes and glue them together to get a surface, like a flat surface. And in those boxes, the foliation just looks like horizontal and vertical. And the joining points of the boxes are the singularities. And this is something I'm going to use in a minute. If you're in the same stable leaf, then your distance goes to 0 as n goes to infinity. This is not correct. This is the other loop. They're transitive. Now let's. Okay, so now I'm going to go back, and now that we know what a pseudoAnosov is, I'm going to talk about applying the previous theory on eigen-transverse arc cocycles, etc. So maybe we could break here if you want, and then afterwards I'll come back and explain how to put the general theory to work for pseudoAnosov maps. And what you get is these transverse arc things turn into measures and Holder distributions. And so that's all to come. Have a break.
10 minutes.
10 minutes. So let's be in this situation now. So we have a fair amount of structure. We have a pseudoAnosov map and its action on homology. Let's say it has an eigenvalue lambda outside the unit circle. All right, and from this, we construct one of these eigen arc functions, or else we have this map in the cover, abelian cover. And we want to investigate what that means. Well, the first observation is that, let's say we're in the stable foliation. All right, in the stable foliation, things have to shrink exponentially. But on the other hand, this is an eigen object. So when you hit it by the infinite, it actually expands. So if you're inside a stable leaf, then this must be dead zero. All right. So what that tells you is that the decomposition elements look like this picture. That typically, the decomposition elements look like a union of stable leaves, typically a counter set cross and counter set across the leaves. All right, so this is the first observation, that if you are in a stable leaf, then your value must be 0 of this eigenvalue. It's because this guy is bigger than 1 in absolute value. All right, so what does this mean in terms of the usual language of foliations? It tells us that we're 0 in here. So if we have an arc and we holonomic it, so this arc goes to this arc, but this must have the same value, but these guys are 0, so this has the same value as this. All right, so it turns out that because this is an expanding eigenvalue, this eigenstructure, this eigentransverse structure you're building that measures some way, assigns numbers to arcs, is actually holonomic invariant. All right, we slide along leaves, the value doesn't change. Okay, so now the question is, what kind of transverse structure is this actually to the foliation? All right, so what do you do? So let's pick one of these guys. Let's parameterize it, pick some parameterization. Remember, it's independent of parameterization. We pick some parameterization and we build the commutative distribution function by we integrate the gamma t, and that gives h of t. So this gives a nice function like a commutative distribution function. All right, so what property does this guy have? All right, so we're going to study this to tell us what kind of object these guys actually are. All right, well, the map, the pseudoAnosov, stretches transverse things by lambda with respect to the measure, which we can assume is arc length. All right, so if we act by the map, all right, then two things are happening. On one hand, the arc cocycle is expanding by mu, but the argument when we move, so the arc cocycle expands by mu, but the distance on the manifold expands by lambda. All right, so this commutative, sorry, I can't say this word, this PDF function satisfies this kind of scaling. All right, so this kind of scaling is common in these semi-conjugacy stories, where you have a semi-conjugacy from something of bigger entropy to lesser entropy, or maybe it's the other way around. So you have bigger entropy to lesser entropy. It has to be that way. All right, so you get this kind of scaling. Now leaves are dense. So again, this is much trickier than this, but this is just the heuristic. So this, whatever this H is, it has this kind of scaling everywhere, or at least on a dense set of points. Now, lambda is different than mu. Well, if lambda equals mu, then we're a different story. All right, so this is happening. So you have to think about a real valued function which does this kind of scaling at a dense set of points. All right, and then you conclude that this can only happen if it folds up everywhere. Right? I mean, you have to stretch, when you're stretching out here, then the image is stretching by something less. Okay. So everything has to fold up. All right. And so again, you have to do some analysis here. And when mu is, again, this is the case when it's strictly less than lambda, you can show its Holder. Remember, this is less than this. This is the Holder exponent. But it's not Holder for any larger exponent. It's nowhere differentiable, nowhere locally bounded variation, nowhere locally injective, etc. So what this means from your basic measure theory, that we can't extend it to a measure, right? So it turns out you can extend this to the measure if and only if it's BV, right? Standard fact and analysis. So whatever this guy is on this guy, if mu is less than lambda, it's not a measure. Right, because of all these properties of the cumulative distribution function. All right, so the question is, what is it? All right, so what it is a Holder distribution. So we have this much Holder in our distribution function. So you can make sense if your test function here is some Holder coefficient that's bigger than 1 minus mu, okay, then you can make sense of an integral like this basically by writing down Riemann sums. All right, so what's the conclusion here is that what this guy builds for you is so you can take the integrals of Holder functions defined on your arcs, and the guy is holonomian invariant. So instead of a holonomian invariant measure, you have a holonomian invariant Holder distribution. All right, so let me remind you about the setup for these guys. So if you have a measure, then the dual objects, I mean, you have a continuous function. Let's go with this way. You have a continuous function. The dual object is a measure. Right now, if you have a smooth function, then your dual objects, C infinity, are Schwartz distributions. So this is, and those are the most of it. So these are sitting between them. You have Holder functions and you have a dual object on the space of Holder functions that's holonomic invariant. So it's some kind of distribution. It's not as regular as a measure, but it's not as bad as a general Schwartz distribution. Okay, so that's what these guys build for you, holonomic invariant Holder distributions. And in the special case where mu equals lambda, then H is actually monotone and phi is then a linear functional on continuous functions. So it's just our favorite measure. So if you run through this whole object and you consider this eigenvalue, then what you get is the invariant holonomic invariant measure. All right. So again, this is usually done using the Markov partition. All right. So this is what it buys you. And let me state this as a theorem then. So we start with a relative pseudoAnosov on a surface with action on H1. So each unstable eigenvalue gives rise to an eigenpath cocycle, which is holonomic invariant to the stable foliation. These are lambda, sorry, mu bigger than 1 in absolute value. And what we did is we used it to construct a transverse holonomic invariant distribution. And this distribution is dual to continuous functions instead of just Holder function, all Holder functions instead, sorry, to continuous functions instead of just Holder functions, if and only if the eigenvalue you chose was the dilatation. All right, so this is in this special case where you have more structure. This is what the eigenvalues off the unit circle value in terms of the structure on the manifold itself. And of course, you can just use the inverse on the unstable foliation for stable eigenvalues inside the unit circle. Okay, so that's, even though in the general topological case, you know, you get wild things. In this case, you get a fair amount of well-behaved structure. All right, so how do you actually prove this? And so, as is usual in a talk, you basically you make a fib to make it understandable. So the way you actually prove all this stuff and the regularity is you use the usual trick of using a Markov partition. All right, so the Markov partition has a subshift of finite type, and the leaf space of the stable foliation corresponds to an equivalence class on the one-sided shift, and you have to connect the eigenvalues on homology to the eigenvalues on the Markov partition, which has been done for us by various theorems of Frank's and other people. And then at the end, you in fact are in a fairly familiar situation, is that the Holder distributions you're constructing are actually eigen for the dual action of the Ruel-Frobenius operator, which Mark has told us about. So anyway, once you take the whole thing and change it to a question about eigen values and vectors for subshifts of finite type, you define a function on the subshift of finite type. Basically, it's defined on blocks and it has certain additive properties. It's eigen, and then you run through the analysis and you find, the appropriate dual Holder structure. Okay, so that's how the proof goes, and let me give you some references here. So as I mentioned already, Frank, Schub, and Fatigue. Symbolic, there's a number of symbolic results are very closely related to the actual symbolic side of the story. And Monahan, and we have, anyway, so this is all, this isn't, of course, built into the relation. There's a fair amount of literature, but usually the points of view are different. This is strictly symbolic. This is symbolic to Danwin. And the thing I'm doing here is to connect these all things together. Okay, so here's a nice example that's due actually to Gavin Band. So we're going to construct a special pseudoAnosov map, which just kind of tells the story for us. So the characters polynomial is Z4. And let's say it's, well, the space is Z4. It has a degree 4 polynomial. let's assume it splits over the integers into a pair of irreducible quadratic factors, right? So so because we're on a closed surface, the actual homology is symplectic. So you always get your eigenvalues having this relation. There's just 4 of them. And so we put all these pieces together and we get 4 semiconjugacies. Each one of these are the stable, these are the unstable. We put them together. And what Fatih showed is that, in fact, the semiconjugacy splits into 2 pieces because of the splitting of this polynomial. And you run through the algebraic topology that, in fact, the semiconjugacy in the T4 actually splits into a pair of semiconjugacies, one corresponding to lambda, which is, of course, the expansion constant, and the other to this other eigenvalue. All right, so you get a pair of toral automorphisms, one corresponding to these eigenvalues and these. I think I have a picture here. So here's the splitting. So you have a semiconjugacy onto these 2, right? And we'll also into their product, of course. And one of them is really nice. All right, so the one corresponding to the expansion constant, there's a theorem of Franks and Ritkin that, in fact, it's a branch cover. Right, so there's a finite number of branch points, and this is extremely nice. So this is the one corresponding to the eigenvalue inside smaller, it's still outside the unit circle, but it's not the expansion. So by the theorems that I've been telling you, this semiconjugacy, what the joke is, it's called the evil twin. So the semiconjugacy, it's still Holder, but it's no more Holder than this. This semiconjugacy is nowhere differentiable, nowhere locally injective for BV. And then you prove using a theorem of Oversteegen that the typical point has a Cantor set inverse. So density delta set here, typical inverse is a Cantor set. All right, so this is kind of encapsulates the story that when you have eigenvalues in, they're hyperbolic, but not the expansion concept, you still get semiconjugacies, but the regularity is much, much less. All right, but still there's enough structure to give you transverse Holder distributions. Okay, so that's the end of that story. Now, if you're old enough or British enough to have watched Monty Python, you'll understand when I say, and now for something completely different. So I'm going to tell you about a fluid mechanics application. And back early, the first, I did it twice. I showed you a fluid mechanics experiment where we mixed the map with the pseudoAnosov map, right? And I said, for the pseudoAnosov map, you can use the whole theory that I've been developing. So I want to take that theory and push it and get some estimates on a particular class of fluid flow, use the expansion and our understanding of the pseudoAnosov maps to prove a theorem about real fluid equations. Okay, so if you remember what I've been telling you, we have this theorem that if you have a pseudoAnosov stirring protocol, then the dynamics persist, but there could be on this small set Y, right? They could exist on this small set Y. All right, so it's very hard to predict how big this set is. So you really want to understand the fluid and its motion in the disk. All right, so now we've dropped the dimensions and we're in a very simple case. So you really want to understand the dynamics in this disk as you're trying to do fluid mechanics. You're not really happy if all you know about is a zero measure set. All right, so rather than invoke that theorem, we're going to use some kind of coarser behavior. And that coarser behavior is the expansion of non-trivial arcs. And they're going to expand at the expansion rate. So this is a real floppy kind of topological thing that happens in pseudoAnosov classes. And then I'm going to apply it to Euler's equation. All right, so first let me tell you what the growth rate of curves are. So this is a standard notion. All right, so first we're only going to think about what are called topologically essential or non-trivial curves. So that means it's looks like this or looks like this. And so what it's not is no homotopic or boundary parallel, right? So we really looked at curves, which are curves or loops, which see the topology. And we're going to always take the least length in the homotopy class. So you can use a Riemannian metric if you like for that. So let's L top be the least length amongst curves homotopic to it. So if it's a simple closed curve, then maybe you tighten it down to these guys, you slide, but you have to keep the endpoints on the boundary. All right, so we have a normalized length after n iterates. All right, so we iterate this curve. It wraps around this three-punctured disk or disk with three boundary components. And after the nth iterate, we normalize, we get this quantity. All right, so we're computing the growth rate of curves, but in terms of homotopy. Okay, so here I think I drew a picture here. You know, we have this curve and we tighten it down and compute its length. All right, so that's what we mean by the length of a curve. And here's something that goes back to Thurston, that if you have a pseudoAnosov map, it forces things to grow in a very kind of macroscopic topological way. All right, so what it means, there's a constant, which is our lambda coming back, and a pair of constants here, so that if you have any essential curve, its growth rate is bounded between, it's an exponential rate, and it's bounded between these two guys. All right, so if you know a little algebra, then this lambda, you can think of this whole thing in pi1 and code essential words and essential curves in terms of words, and it's telling you about the way words are growing in length in the fundamental group. All right, so the experiment, remember, we had this guy, I think I have another, here's a picture. So this is after 9 iterates. Yes.
Do you really use the Euclidean lengths to compute the lengths of the minimum lengths?
You can use Euclidean, or you can have a Riemannian metric and take the infimum over smooth curves. You can do that way. Right, I mean, yeah, it's the infimum, so we don't have to worry about non-rectifiable curves or all that craziness. Okay, good, thank you. Okay, so here is this. Remember, this was a picture. This is glycerin. This is dye. We've switched these guys in the pseudoAnosov way 9 times, and lambda was 2.62. Again, this is, I didn't say this, but this is basically 2111. You do 2111 on the torus and mod out by the Weierstrass P function, you get this guy. Right, so it means that if we could measure the length of these guys, if they originally were a centimeter and now there's about 6,000 centimeters long. Of course, this, diffusion has taken place, which is the point of the mixing. But so that's, so this shows you a picture of this exponential growth rate. All right, here's some other pictures stolen from Matt Finn and Jean-Luc Tifo. Here's a picture of a braid. So you think of this stirring happening in space-time. You start with this curve and take its image, and you see it does like that. So for any of these pseudoAnosov stirring protocols, you get this exponential growth rate of closed curves, or in fluid mechanics jargon, material lines. All right, material lines in the fluid, like a dye line. Okay, so mixing, this is just kind of physical motivation. The reason this came up, I was visiting a mechanics department, and they wanted to understand how to mix things properly. What they were interested, they wanted an area preserving map with no elliptic islands, because elliptic islands correspond to things where nothing mixes. So I told them about pseudoAnosov maps, and then we did these experiments. But so mixing means just what you want. It doesn't mean mathematical mixing. I'm talking about physical mixing, your cream in your coffee, etc. And we're going to use dynamical systems model, so we're going to ignore diffusion and chemical reactions. So the honest story is that, eventually the mixing is done on small scales by diffusion, but we're ignoring all that. And so the point here is when you have close layering of lines, then at that small scale diffusion takes over. So good mixing is characterized by big gradients where things which once were far apart are close together. And that'll be the theorem. Okay, and again, we use iteration, periodic stirring. These are all simplifying assumptions. All right, so as I said already, we consider the gradients of the material being mixed. All right, so you stick some stuff in there, like dye or cream or sugar and chocolate that you're making. And alpha of t is a real valued function, which is measuring what's the density function of the stuff you've put in there. All right, so in this case here, we had, in our experiment, we had a pair of lines like this. And so alpha of t, well, it was alpha of t looks like it's 0 here, then it's got a big bump here. All right, and then we push that forward. Again, in fluid mechanics language, it's called an advected, it's a passively advected scalar. And the idea is that if the gradients are getting big, right, it means, you have these bumps here, but if you have multiple close layering, then you're going up, down, up, down, up, down. So the gradients getting big means that you're going to mix well. All right, so what our theorem is going to be about is to connect the exponential stretching of, well, as I said, this is the material line, with the growth of gradients. All right, so again, this is all going to use the pseudoAnosov theory and this theorem of Thurston on growth rates of advected, if we use that language. Okay, so here's some more formality. So we think we have to make a model for a mix. So the fluid motion is phi sub t. It's just a one parameter family of diffeomorphisms. We have a function, time-dependent function. It's, again, this is jargon. It's passively advected scalar, means it's just pushed forward. It's just in our usual, differential topology way. It's what it looks like after time t. It's just a push forward of the initial condition. This just says its derivative along trajectories is 0. So as I said, it's really just standard push forward. All right, so this is what it means for a scalar to be advected. This, this agrees, again, ignoring diffusion and chemical reactions in it. So we just have some quantity and we push it forward in the simplest way. Okay, so here's the theorem. So now we're going to stir it. So think of the experiment. We stir it with the pseudoAnosov protocol, and we have an incompressible fluid. All right, so incompressible means area preserving. All right, so just a fancy way to say that the Jacobian is 1. All right, not a fancy way, a physical way. And let's say we have a passively advected scalar. And now we need a hypothesis because we're actually going to prove a theorem. I'll tell you where this comes from. Is that alpha 0 is a generic C2 function. So I'll explain why we need this condition on the scalar function, which is measuring how much stuff we have. Then the theorem is that there's a pair of positive constants such that the gradient, well, the sup norm of the gradient is growing exponentially fast. The L1 norm of the gradient is growing exponentially fast. And the exponential, you know exactly how fast it's growing, at least a lower bound, being the dilatation of the pseudoAnosov protocol, which is the largest eigenvalue of some primitive Perron-Frobenius matrix. All right, so as I said here, you can think of these in more fancy fashion, C1 or the 1-1 topology go to infinity exponentially fast. All right, so this is some kind of the growth, I said, I'm plugging the growth of the gradient is growing exponentially fast, which is some kind of mixing Again, not ergodic theory mixing, but physical mixing. All right, so here's the proof, at least the idea of the proof. So where do we use the dense open set in G? So we choose Morse functions. All right, so Morse functions we know about. You know, the behavior at critical points is positive, is not degenerate. And we want to make it so that there are bands of level sets somewhere. So you can do this with a C2 open dense set that the alpha that satisfy this have bands of open sets, either between boundary and boundary. Again, you just use standard differential topology. All right, so here's the argument, and this is just the local argument. We hit it with our fluid motion. So what do we know? Well, the level sets of the scalar are arcs, and they're topologically non-trivial arcs. All right, so the image of this band is really long. All right, but remember, we assumed it was area preserving. So the area of this guy is fixed. So you have something that's really long, but its area is fixed. All right, so the only way it can get really long and have the area fixed is that these curves get closer and closer together. It has to get squeezed down somewhere to do this. This is basically just calculus 3, as we have in the US anyway. All right, so the level sets bunch up. Well, what happens if level sets getting close? What happens if level sets with different values get closer and closer together? Well, that's exactly saying that the gradients are growing. All right, so in fact, that's the heart of the argument is things get long, the area is preserved, level sets get close together. In terms of calculus, that means gradients are going to infinity, lengths of things are growing exponentially, and therefore the gradients are growing exponentially because the lengths are growing by this dilatation constant at least. All right, so that's how you prove it. And now this is a general fact, and now I'm going to apply it to Euler flows. So I won't write down the equation, but Euler flow, you ignore the dissipation, right? So it's like doing friction-free classical mechanics. It's, you know, and in fact, in the appropriate setting, it is the same as friction-free in infinite dimensions. All right, so let's apply it to Euler's equation. All right, so here's Euler's equation, incompressible Euler's equation. So there's some pressure. The pressure is like a Lagrange multiplier to keep this constraint in case. Let's assume we have constant density. A solution to this guy is called an Euler flow. Well, all right, so this is an equation for the velocity field, the vector field, and then you have to integrate it to get the flow, you know. And the curl of veridicity is this guy. This turns out to be very important in the understanding here. And so again, if you know anything about these things, you got to worry about solutions. So here in 2 dimensions, we get we are doing okay, right? So this is just reassurance that we're not talking about the empty set. So in general, let's just assume, as one often does in this business, we have the regularity, we have a global solution, which stays as regular as its initial data. All right, so that's all quite deep, and I'm ignoring all of it. So here's a wonderful theorem about Euler's equation, which saves me, because I don't have to think about Euler's equation. So Euler's equation there's a whole theorem due to Helmholtz and Kelvin from 2 centuries ago now, I guess. You can use topological methods. All right, so this is the amazing theorem that a 2-dimensional area-preserving fluid motion is Euler if and only its vorticity is passively transported. All right, so this is a little fun to think about. You have the vorticity at this point. It's some amount of twisting like this, so rotation. And then at a later point, you want to understand how much rotation there is. Well, if this point flows to this point, then the amount of rotation is the same. And then there's another condition is you have to preserve circulations around the boundary. All right, this is if you have a region that's multiply connected. All right, so very old theorem. And it's a little tricky because is basically the snake is biting its own tail, because the vorticity isn't a separate quantity that's being transported. The vorticity depends on the velocity field. The velocity field is creating the transport. All right, and then the transport has curl. So it's kind of self-referential, but nonetheless, we can use it here. All right, so I had to have, living in Florida, I had to show you these pictures. So you know about transport of vorticity. So here, unfortunately, there we are here. Here, there were several hurricanes. So certainly with a hurricane, you can see the vorticity being transported, there's dissipation and there's heat pumping, but in principle, a more common one is when you're canoeing or kayaking, you pull your paddle through the water, you see that little swirl goes downstream passively, remaining a swirl before it gets dissipated. Okay, so there is our condition on Euler equation, okay? And now we know that what happens to passively advected scalars, but vorticity is a passively advected scalar. And so we have a theorem about the growth of the gradients of the vorticity. All right, so here's the theorem. So this is, I said this already. So Helmholtz-Kelvin says vorticity is a passively advected scalar. So we use the theorem above to get this. All right, so now what do we need to know? So we have a time periodic protocol of pseudoAnosov type. So that means we have a bunch of disks here, we move them in some complicated fashion, and then we hit it with our big theory and we declare it's pseudoAnosov. And we then have a fluid motion given by this. Now again, hypothesis, our initial vorticity now isn't anything, it's a generic C2 function. All right, but then there are positive constants so that the gradient of the vorticity now, so we got a couple derivatives going on here, but the gradient of the vorticity is growing exponentially in both the sup norm and the L1 norm. All right, and again, there are programs out there where you feed it the motion of the stirrers and it spits back lambda for you in a few seconds, or even less than a second. Okay, so you get these estimates, and again, you can write them in more fancy ways, recognizing that this is in itself a derivative, that the Laplacian is growing exponentially, the C2 norm is growing exponentially to 1. So in particular, you get a conclusion that's sometimes that the velocity field is not time periodic. So there are kind of two extremes in fluid mechanics. You have something called Stokes flow, which our experiments look like, where as you move them and then you move them again, it's periodic. But the reason I needed to go back and use that topological theorem about Thurston is that this is not a periodic collection of functions. This is what all this stuff is telling you. As you move the protocols, something's growing. So it's not just you're starting and going back and doing the same thing over. All right, so you have this exponential growth. Okay, so there, someone told me no one minds if you stop early, so that's what I have. I won't, well, let me stop there. Thank you.
I could probably ask one. I guess these path cycles, do they give anything good in higher dimensions?
Yeah, so I've never thought about it. I mean, I think definitely yes. I mean, I think you may need a codimensional one foliation. So that, and I need a complex argument. So I think the answer is yes, but I don't know how to. I have not thought about it or formulated it properly.
Yeah, because these classes remind me the rule 7 classes for Anosov fields. Are they related? Like currents and stuff.
Right.
I don't know. Okay,
Yeah.
Just naive question, I guess.
Well, so So I didn't, so the measured foliation is, there's lots of interpretation. One is as a current of integration, because you can integrate forms against, that's like Rel-Sullivan. And the foliation is eigen with respect to that action. I don't think, yeah, so probably the transverse distributions also give you a current of integration, which is eigen under the action. So you go from, you know, you have homology, then you have Durand, and then currents of integration send you back to, they're dual forms, and that puts you back to homology. And so, yeah, so yeah, you're going to get a current of integration. So it's going to correspond to the core eigenclass in homology. Yeah, it's going to be much less regular, but yeah. Long break.